So I guess we're just going to go ahead and get started here. Hi everyone, this is Ron Batum with Atlanta Functional Programming. Welcome to another Common Lisp study group. Today we'll be discussing you know, sort of the nuances of the special operators as discussed in Chapter 20 of Practical Common Lisp. Now, what are the special operators? Really, Peter doesn't give a real I would say good uh, explanation as to what the special operators really are. But from what I gather, and this is from a couple of books, I've read this in Common Lisp the language as well as ANSI Common Lisp and a few others. They're really, I guess they would be. I would consider them the most indivisible like operators that you will have in Lisp. Like, you have to have these available. A lot of the Common Lisp infrastructure, in fact, are built on top of these operators. So you can almost consider them over almost like a sliver of assembly on top of what you could consider to be like the standard Common Lisp library. Like I mentioned, like the book mentioned, there are 25 of them. Now, this is not including, and this often actually happens even in other languages, the standard arithmetic operators that are available, that should be available in every Common Lisp system. These are actually specific operators that do specific things. They control different parts of the Common Lisp system itself. Everything from controlling the evaluation of particular codes, as we will start seeing in the beginning, to iteration constructs are often used, to low-level functions that could be leveraged to implement your own, exception handling system, as was indicated in the beginning of the chapter. So these, if you sort of understand how to use them, some of them are very rarely used in practice, but they might be available in like existing code bases. You can get a better understanding as you start spelunking through some of the Common Lisp code bases that are out there, sort of how, especially older code bases, how the language evolved over time. And it actually shows the strength of Common Lisp because you are able to, because of these operators, really, I would think, be able to grow the languages and add additional new constructs. Now, those of you who are like used to saying like, can we add a type system or typing things, these are not dealing with those kinds of issues of implementing like languages and extending the system to improve types. Those things we'll discuss in a different talk. This is specifically for controlling and transforming execution of code, and that's what we'll get started with. So the first category I would say that we'll be discussing is the control flow, special operators. Now, we've already seen all of these. And I've kind of, through earlier CL study groups, I've sort of hinted at this, especially with some of them that a lot of constructs can be built on top of them. One example is that we've already discussed when we were discussing macros, the if statement. The if statement basis really is the basis of almost all Boolean-based, control flow conditionals that are in Common Lisp. So, like, if you expand, for example, when, which we've seen in the past, you'll notice that it will automatically expand into an if condition. The same thing goes with, unless. Unless will just simply change from, the if condition to the else condition, because obviously unless is not if. And you could build this, if this wasn't even in the language, you could actually build these control constructs yourself. One of the most primitive ones that are actually available is actually quote. Quotes is actually one of the primitive Lisp operations, and all it does is it prevents the reader, the evaluator, from actually evaluating an S expression that is being passed in, or any data for that matter. So in this example that I have here, I'm just passing in a standard addition of 1 and 2 to quote, and when I try to print it out, you'll see that it will actually just print out the S expression. That's because quote's telling the evaluator, okay, until the end of this expression, anything that's in here, do not evaluate it. So we can also add a bunch of code in this guy, like with a prog n, and it will do the same thing. Like if we do 2 plus 3, 1 times 2, you'll see that it will just go ahead and print it out sequentially. And that's actually very useful to pass data around. Like if you wanted to treat code as data, since code's already an S expression, you could just quote it, and boom, you have your data element that you could just pass through to different functions. It's particularly useful in terms of like the data code as data thing. I often uses it for things like special purpose REPLs that I build into my applications. But there are other cases where it will become quotes very, very useful to use. The final thing that I would say is prog n, of course, which we've already talked about multiple times. I don't need to really say much here other than for review. If people don't remember, prog n is the operator that essentially tells Lisp to execute the next series of S expressions sequentially, one after the other. So, in fact, defun actually uses essentially internally. You can actually see that it's using a prog n type structure to actually execute different operations sequentially. So in this example, as you can see, I just simply wrote 3 statements, and it prints them one after the other. So a lot of that is kind of review from what we've seen in the past. Again, even in the lexical section, some of this stuff is kind of review. We've talked about a little bit about let expressions, particularly the difference between let and let star. Let, you can't actually, like for example, use x in this expression. It'll actually complain because it'll say x is not bound. The reason for that is the environment internally doesn't keep track of a scope table, so this change actually is unaware of what x is, because until let is completely defined through this statement, none of those symbols are actually available for use. So if we use it this way, you can see that in this case we're able to actually use x and y after they're both defined, and then evaluate that expression. Now obviously, if you want to use variables that are previously defined, but you don't want to define them globally, you would use a let star, and you could then leverage that to actually go ahead and use previously defined variables in definition of new variables that you could then go ahead and execute inside additional S expressions. So this is definitely a review, but one thing I will say that's kind of maybe unfamiliar is because we never touched basis on it, is set Q. Set Q is used to actually allow you to go in and modify variables in the lexical environment. However, and I don't know if this is still true, but for the most part, set Q is deprecated in almost all situations. You would want to use set F. Set F is actually does what set Q does to as well. I don't know if there's a situation where set Q is preferred over set F, but from what I've seen, at least in code bases today that I leverage, almost none of them use set Q. A few of them. Right. So Yeah, I saw that. There you go. I was gonna go in and change it in. Yes. That's a good question. Part of it is of historical consequence, I would say. There were existing Lisps at the time that Common Lisp was being standardized, where let had a clear, defined set of semantics, and they didn't want to disturb any existing code that was being compiled over into the newer Common Lisp compilers. Um, that being said, there are cases where let is good enough that you don't almost never want you most never need a let star because you're not defining variables in terms of each other. But I don't think it's an efficiency thing. At least I don't believe so. Um, I haven't seen any issues. In fact, and we'll be touching a little bit later on this. The same thing will go for actually for inner function definitions. That is flet versus labels. So some folks have asked me in the past, well, why didn't labels just become the new flet? And I honestly think it's more of historical consequence that they didn't replace it, because at the time that they were being standardized, they wanted to port over a lot of existing code into using Common Lisp, and that was just a set of semantics that was already available in those Lisps at that time, and they didn't want to go and disturb and change those code bases because they were probably too large. Michael Fiano, do you have anything to add to that? Does that make sense? Let you can use with the functional programming paradigm, right? I mean, you often can actually encourage, because if you're doing like say closures, for example, leveraging let. At least I don't believe you can do a closure in Common Lisp without a let and a lambda. Maybe with a lambda and a lambda within a lambda. Maybe you could do it that way to get some additional state. But all the examples I've seen, at least in CL, to do a proper closure at least, you would have to use let form of some sort. But I have to go and review let over lambda for that one, to be quite honest with you. um, right. Um, So since we got on the subject, the same thing that Michael Gargano brought up about let and let star, the same we actually have functions that allow you to define. I mean, operators that allow you to define inner functions. That is, functions within the scope of a function. They're not polluting the namespace, the global namespace at all. And there's two types, just like let and let star. Flet allows you to just define inner functions, but you can't define inner functions with in terms of the of other inner functions that are being defined in sequence. So, like to give you an example, we have a simple, my double here that will just print, double of a number that's being passed in. But if we wanted to use, say, increment done double that takes in, that just calls my double with a function passed in like this, you will see that if we just even tried to compile this, let alone use it, you will see that it'll whoa, it actually did not complain. Hold on one second. Now I have to go and see if it probably is because it's optimized out. Yeah, when you actually try to use it, it'll try to see if it's bound, and at the time that it was bound, my double will complain, just like the X and Y. So honestly, in this particular situation, this is my own personal preference. I never use flet because I, most often than not, am always thinking about using functions within other functions. In particular, if you want to like be able to like test individual functions within the scope of it and get a better understanding, I tend to like using very small functions and use labels to define them within each other. That's just my way of developing. I don't know honestly what the best practice is, but here you can see that with labels, you can define it within each other. So in this example here, just highlighted, we're incrementing the value and then we're doubling it. All right. You can see that we are actually, wait a second. I just realized that I made a mistake there. What I wanted to do is call increment value here, but it's the same thing. So you can see that in the labels, I'm actually leveraging in increment and double the previously defined increment value, because labels is actually automatically putting it into some table and then making it available immediately for other functions to use as it's going down and evaluating it one by one. Flet doesn't do that, and it's kind of useless in my opinion. I don't know either. Yeah, no, you're absolutely right. You think that they would have labeled labels as flet star, but instead they kept it. And again, it's one of those things where you're just like, okay, this historical cruft that's in the language, they have some really beautiful features. They should have just decided to make like a, you know, I would say a deprecated namespace with all these functions, all these operators in that namespace, and then define the standard namespace with in terms of those ones until they decide to move everything over. So that way all new code will use a more consistent naming scheme. But you know, if you there's a I think it was a there's an interview by Peter Seibel, I'm forgetting, it's on SoundCloud somewhere, where he talks about common Lisp standardization. And he said that those 10 years from 1981 until the standard actually sort of came out in 92 in its kind of final forms, and before it got actually standardized in 94, a lot of it was like politically motivated. And some people wanted their code bases to be completely pristine and untouched, even though they moved over to Common Lisp. And a lot of compromises were made because of that. And this is one of the compromises that we clearly see here, which is I think when I originally looked at it, it was 7, which is, and most of them, what was funny, if you actually look at Common Lisp's history, uh, it a lot of them almost all derived from Mac Lisp from the 60s, which is like, man, if you talk about divergence in the Lisp communities, it was very divergent, it diverged almost instantaneously over a period of 10, 15 years. Um, and when DARPA came in to unify the Common Lisp and create the Common Lisp standard, I honestly think that was kind of a good thing and a bad thing at the same time. Instead of letting the market sort of like decide which I say dialect is kind of like the best dialect out there, they said, okay, you guys, we're giving you too much money for AI research. Unify all the lists together, stop worrying about the system, and start concentrating on what we're paying you for. And that caused a lot of grief with people with existing code bases. One cool thing that's an operator in all of this is actually before we get to that, just to show you guys that I wasn't kidding. Labels can also allow you to essentially define recursive functions. Same reasons for before. It's defining it and making it almost instantaneously available, and it's doing some optimizations behind the scenes to make it available. The other thing that that allows you to kind of manipulate the lexical environment is, and I forgot about this one until I saw this, is symbol macrolet. There is an actual macrolet form, but we'll be discussing that later on. But symbol macrolet gives you the ability to define symbol macros. So what is a symbol macro? This is something that we didn't touch base when we actually talked about macros, so I thought this is a good time, since we're talking about symbol macrolet, to discuss what are they? What are they exactly? In a nutshell, they're nothing more than a shorthand for a particular symbol. That is a particular evaluation of a form. And it does a simple substitution in a code base versus what macro does. A normal def macro actually expands into one or more different forms. So you could think of a macro has a code generator, and a symbol macro, at least this is how I sort of may put the difference. A symbol macro is more of a textual substitution than an actual code generator. And there's some uses for this, especially if you want to use particular mnemonics to represent, like, accessing certain types of certain data structures a particular way. So, like, if you look at this example here, we've defined a list of 5 integers, and we defined a symbol macro to point to essentially the first of the list. And we go ahead and use that to set the first element of the list to 6 and print it out. So when you print this out, you'll see what it's expecting, what we think it would do. This is the equivalent, has the following. So like if you do setf first list, a list 6. So this guy here actually expands to that. And it gives you a nice way of, like, at least labeling particular parts of a data structure. Now, the real use case for this isn't for stuff like what I'm showing you here. This is kind of a contrived example. But one real good use case for this is with, there's what we were using earlier in our discussion about accessing slots. With slots, essentially, behind the scenes could be implemented. Leveraging symbol macrolet has a quick mnemonic to generate symbol macros to make code look cleaner when you're actually generating it internally. So you'll have some nice little variables that actually represent slot value access to a particular object method. Now, you can actually do and define symbol macros not only in a let form, in a lexical form. You could technically do it in the global namespace. That's what define symbol macro is. And this, again, shows another kind of weird thing about Common Lisp, because we've talked about defun, we've talked about def parameter, def var, but now when we're talking about, and def macro, but when we're talking about symbol macros, it's not def symbol macro, it's define symbol macro. They changed kind of like the naming scheme for defining symbol macros. I think reader macros are the same way too as well. It's a define reader macro. It's not def reader macro. So it's kind of interesting that they change the naming schemes willy-nilly sometimes. Yeah, set macro character. It's but This again does the same. This define symbol macro basically gives you the same sort of ability that we were um, doing earlier, which is it's a simple shorthand for actually uh, accessing particular parts of a data structure. At least in this case, there are cases. In the case of with slots, it will actually generate quick mnemonic to access instance methods or accessor methods that can be instantiated on a particular object. But you'll see that all I did in this example is I created a global namespace. I defined a simple symbol macro to do essentially what I did here, which is point to the first element of this global list. I set the list, and then when I print it out, you'll see that it gives us the same results. I will be honest, I have very rarely used symbol macrolet and define symbol macro alone. I almost always end up leveraging it from other parts of the standard library that uses them internally. The reason we're going through this chapter and the reason why this chapter is kind of important is because these operators give you the ability to define your own stuff if you need it and when you need it, but you may most rarely will never need to do this. You may be able to create higher level constructs just using some of the standard forms that are already available. But in those small cases when you do, these guys are at your disposal. All right, that's really the if that's the take home message that you get from this discussion, then honestly, this chapter has done its duty, and I've done my job too as well. So the next thing that we're going to be discussing is local flow of control, which is like how do you deal with exiting out of blocks and scopes, and is there's a way of actually jumping out of a particular block and scope. But to get started, before we start to this, I want to talk a little bit about extents, because this is something that is not necessarily discussed in the book, but this section on block and tag body especially, it's especially important for you to understand those concepts so that you can leverage them rightly for your needs. So in the case of what is it? So I have to go and recall what it is. So with scope, it was you know what? I'm just going to show this to you. This is complements of the Common Lisp language. And let me bring this out. So in Common Lisp, the language, they define scope specifically as the spatial region of the program from which references may occur. And extent is defined as the time interval where references may occur. So a simple example of this is, let's say that we create a function called, our good old standard add function, that we created that adds two variables, right? In this example, A and B are only accessible within the scope of this function, all right? There's nothing can escape from A and B, all right? But when you start talking about extents, it means that there's a possibility within any time interval, all right, that you can access that label, that symbol. And where this becomes kind of important is when you start dealing with things like call stacks, all right? And within call stacks especially, variables may not be accessible, but labels certainly have the possibility of being accessible within a call stack. So this is kind of useful because block and tag body leverages this to give you the ability to do what's called non-local returns. That is, when you're going through and you're in, if you guys are seeing this on in my Emacs buffer, if you're calling func A, let's say we call foo, we call bar, and then we call baz. All right. So internally, if I just show this here, let's say that this is our call stack. Okay. So foo calls bar, bar calls baz. Anything that's accessible to foo, all right, like has in a scoped variable, is not accessible to bar and it's not accessible to baz. But let's say that there's a label in foo that's associated with like a jump point, all right? Bar can actually technically jump out of it and go to that point because it's within the extent of its accessibility, all right? Same thing goes with baz. If you call like go on something that that's available only in foo, since that's a jump point that's accessible within the extent of the call stack, baz will be able to access it and then jump to that point. If the function's out of scope and someone's actually leveraging something that's not in the call stack, that's something that's in the call stack but it's not accessible because the call stack has not been instantiated, what ends up happening is this common Lisp makes an error. So let's give an example of this. With respect to head here and block. Block is takes in what's called a label. All right, it's just a symbol this name is just used to actually provide sort of like a label point that return from can leverage, so it can do a lookup to see where it needs to exit out of the scope. So in this example here, I'm executing printing out +1, 3, and then I'm jumping out, returning from this guy, head, with the value true. So what you would expect from this code piece here is the last statement there, this won't be executed, actually will not get printed out. So what happens when we actually run this thing? You'll see that 4 gets returned, and as we would have rightfully predicted, the format statement does not get executed. In fact, what SPCL does at least is when you try to compile this guy, it actually generates a warning saying that this is unreachable, so I'm going to delete this guy. So, oh yeah, it's a note, sorry. It's basically saying that it's optimized at taking it out and just generating what it actually is going to be executing. This is not particularly useful in this particular contrived example because I just essentially was running in sequence and just abruptly changing it. But you can leverage this in other ways. Like defun actually internally creates a block statement and returns from it. And to show this example is, I thought it would be best is we compile add. Then what I'm going to do is SBCL has 2 different macro expand functions, and if you use other hold on. Oh, thank you. CLTL2. If you use other Lisps, it may be their naming scheme or their namespace scheme may be different. But on top of macro expand 1, which we've discussed when we talked about def macros, there's a macro expand all, which will keep going until it hits the primitive operators. And if we go and, do I think if I just do a defun, add AB, no, it's actually when I call it, I think. No, where was it? It was. I was just doing this earlier. This should have worked. I have an example? I wrote an example here earlier that actually generates a really nice actually this guy might generate a really nice, yeah, okay. Let me try that one. So what I was going to illustrate here is, and unfortunately this is not working the way I expected it to, is you can actually see the macro expansion to a block nil. In this particular case, since this is a simple example, it's not actually generating this. It's generating an optimized version of the add function, which is not what I was intending to show in this example. Yeah, that's right. I could do that, do list. That's right. Do list. Do times. Oh, right. It's not. Macro expand 1. No, that's not it. Do list. Yeah. So do list is another way of doing this. So for iteration constructs internally, what it does is it can actually create what's an actual block itself. It will generate a symbol, an automatic symbol using gensim, and then it sticks the entire iteration construct into a tag body. So it behind the scenes takes your high-level iteration code, whether it be a recursive function that you wrote in tail recursive form, or you wrote it using standard do list, do times, or even loop, and it converts it essentially into a goto in a branch statement, which is what you would expect at the assembly level, by the way, but you would never actually expect it at the at such a high level. But what this shows you is and what I'm trying to get at is that these operators give you the abilities, and especially with the macro facility, that if it didn't exist, you could implement it. You can actually go ahead and add something to it. And that says a lot. Go ahead. What you had a thought? Right. And this is actually really says it all. For an infinite loop, this is all it is, and it will generate very. I mean, the code is almost the assembly code. If you actually do a disassemble of loop, is almost identical to this, minus a few instructions on x86, which is why I will never show it on x86. Just so you guys are aware, anytime you call a function in x86, you generate essentially 40 bytes for the stack frame before it even begins to actually even calling the function. So all that additional code is actually a preamble to actually calling the function. So anytime the disassemble works in in Common Lisp, it will not actually let me do that. Actually, I can do it with 1, 2. What? Hold on. Not 1, 2. Add 1, 2 is what I meant. What? So I have to do a quote lambda. Okay, that's weird. Maybe. So, okay, gotcha. So But actually, I should be able to do a function definition, shouldn't I? I thought I'd go disassemble this guy. Nope. Okay, that's... Ah, I could get rid of it. That's what I could have done. And it's the same thing. And the difference is one is it's a few instructions more if you actually generate the generic add here with the definition, because obviously in this part here it's actually generating the stack frame and moving all the base pointer into the base register and setting it up before it can actually execute the add, and then it pops everything off here in this section. So, tag body. Tag body, we've just talked about a little bit, but to show a very simple example of this is this simple guy that I just wrote essentially iterates through, much like what you would do with do times, but you could, I just went ahead and wrote a simple form that will iterate 5 times. And if you wanted to, you can actually say my do times and create a function yourself that would, generate a form. Although I'm not going to do that here for just because of time constraints and discussion. But one thing I will point out is tag body and blocks, unless you are really creating certain higher level constructs that are not in the standard, are very rarely used in everyday code. You will see it in macro expansions. You need to understand them primarily for expanding the macros and actually seeing what the code's actually getting generated. But in terms of actual usage, unless you're really creating very highly performant code, or like in this example from Peter's book, you're translating an algorithm from a textbook into Common Lisp verbatim, or in the case of, like, say, Fortran, if you're trying to port Fortran code or other code from other languages into Common Lisp, where there is a goto or is some tail recursive operation that you need to implement that cannot be done with the standard control constructs, you can actually go and transform them verbatim into Common Lisp using these lower level operators and then go through the refactoring exercise. So like in this example here, this algorithm S, which is a selective standard sampling algorithm that you can use from a large range of integers, came straight out of the art of computer programming, and it was implemented essentially like a series of states. And what Peter did is he just simply said, you know what, I could just use these as labels and implement this entire code base as a tag body. And he did that. And it's pretty cool to be able to, like, if you look at the textbook and you look at your code, there isn't much difference in terms of debugging, because as long as the textbook is correct and you transformed it correctly from the textbook into code, it should also be correct. Now, if it's being optimized at the assembly level, that's a different discussion altogether. I'm just going to point that out. But being correct in this case is what is why some folks would prefer being able to copy the code from a textbook or some paper or whatever into their language of choice, and Lisp gives you that ability. So if we want to run this guy, for example, we can see how it works. You give, let's say 10. Let's say that our maximum value that we want to choose from is from 0 to 1,000. It will go ahead and generate 10 samples between 0 to 1,000 successfully. Block and tag body gives you this ability to abruptly unwind the stack. So in this example here, again from PCL, we are entering a function and we're calling 2 additional functions, but the innermost function, in particular in this case, baz, it's the one that actually does the fun call to this closure that's being passed into bar. Okay, so if we run this guy, if we run foo now, what you're going to see is it's going to enter foo, it's going to enter the block, it's going to enter bar, and it's going to enter baz and then pop out and exit foo. All right. So what it automatically did from that fun call, because we have this label, it popped up the stack, just went to the label and exited the block altogether. And this is it's pretty cool because it gives you the ability to essentially implement kind of like an exception handling mechanism if you really needed to. And additionally, this particular example was illustrating what I was trying to talk about earlier about extents. Because A is within the extent of baz, all right, it went ahead and was able to successfully execute that jump point, and it was able to return from that block altogether. The same thing goes with tag body. Like, let's say that we redefined foo with tag body instead of block. Well, if we run foo again, we haven't changed any additional thing. We're just running foo again. You'll see that it will do the exact same thing. Because exit foo is a label within the extent of the call stack, the jump point can actually unwind the stack to that point and then continue execution. A couple of things, though, to note about this. The type of extent that blocks and tag body has is what's called dynamic extent instead of lexical environments which have indefinite extent. And what that means is the lifetime of a label is only within the call stack of that label. So if you exit a function signature, a function, all the labels within that's accessible within that function are no longer accessible. All right. So what that means is if you return a closure, let's say that you decide at some point to have returned this closure, like if you for example, put this in a let form instead of passing it directly. All right. And we do bar x. All right. And then we do one more thing. Let's say that do bar x and we return it. Do this way. Sorry. We return it. There we go. That's what I was looking for. If you assign this to any variable, and let's say you call it outside of the function, what it's going to do is, and what it's going to end up doing is, it's going to complain. It's going to your Lisp is going to throw an error, and it's going to display a message saying that the label is not bound and it's not even available. So I'm going to leave this as an exercise because this is I think you guys have to try using this because it'll give you more of exposure into how extents really works inside Common Lisp, and it gives you an understanding of how the stack kind of works inside Common Lisp as you start going deeper and deeper and deeper into a call stack. But it is certainly something that is pretty neat to see, and once you understand it, you'll start really asking different questions. The book talks about throw and catch. I really don't want to discuss throw and catch because they're almost never used. At least it's enough that I think I will be doing you a disservice by talking about them than actually talking about them, because um, they're there primarily for historical reasons. Um, they are different than the try and accept conditions from other languages. So leveraging them or even trying to think about them or seeing them might, confuse you more so than actually help you. Um, they are, and they're particularly kind of just be aware that they exist. All right, but they're not. They're dynamic versions of bro and block and return from, and uh, never use them. Just if you're going to do exception handling or of some sort, use conditions. Just go ahead and use conditions and just be done with it. Don't bother even. I can't even stress this enough. Don't even worry about really understanding why they're there still. Is that a good sentiment there that I'm stressing there, Michael Piano? Okay. Um, the the final two things I'm going to be talking about is really unwind, protect, and then we'll touch a little bit bases. We've talked about multiple value before, so I don't think I'm going to reiterate that particular thing again. Um, but we will certainly talk about Unwind Protect, because Unwind Protect is something that almost everyone should know about. Uh, what does Unwind Protect do? So, in the most simplest form, Unwind Protect essentially allows you to specify a form that must always be executed after a particular set of forms have been executed. So let me show you the form of how this looks like. So this is what Unwind Protect actually looks like. This is your general form of Unwind Protect. You have a form that it generates, that it's going to evaluate, and let's say that it's popping off the stack, or it's executing the stack, or it's evaluating it, right? Then, if at any point you decide to return, let's say that there's a block in there that returns from it, and it returns from your Unwind Protect altogether. Prior to actually exiting the Unwind Protect form, the cleanup form will be actually run. An example of using this is really resource management. Let's say that you're trying to implement, your own resource handler, like with database connection is the example that the book gave, that I think is probably the easiest thing to just go through. In this example, what it's doing is it's opening a connection, it runs through a series of potential operations, and then it closes the connection, okay? Because you almost always want to close your database connection unless you're like leveraging like a pool of connections, at which point even there, the last form, when you're exiting an application, let's say you're killing a server or whatever, you should actually go through the process of closing your database connections. I'm not going to stress that enough too, because that's actually, I've seen that in real code where people forget to close their database connections, and that caused me grief because of unnecessary handles being not used and making it hard to actually leverage the database. So what uses of this if we design this? Well, if you leverage this with database connection, and you try to do some stuff and do more stuff, here your application user can completely do whatever the hell he wants, and he can be guaranteed that when he leaves the with form, the database connection is closed. So he doesn't have to worry about it anymore. Same thing with with file. With file underneath, what it does, it's an unwind protect that closes the file after a series of forms are actually generated. It does the exact same thing as with database connection actually does, with the exception of closing. It closes the file handle instead of the database handle. Almost all the with macros, in fact, follows this pattern. They essentially do a let, they open up the file handle, they do operations within an unwind protect, and they close it within that unwind protect, and that's it. You can look at any other ones. There are plenty of examples that are available online that will show this. And from the stuff that I've seen, this is actually a very standard macro pattern that's often used. Everything's within a let form and uses unwind protect. So if there's one thing that you can really guarantee on is this guy, because Unwind Protect is kind of like finally in Java, or finally in, I think even Python has finally, if I'm not mistaken, where you can essentially close off your resources. This is actually why I like to stress it, because this is often ignored. Unwind Protect is probably one of the best features I've actually seen, because a lot of finalies and stuff, it depends on the compiler if it actually says. This guy is actually well defined in the spec, and I don't think there's any special characters. It deals with non-local exits, it deals with jumping out of forms, it deals with exception handling cases with the condition system. Just use it. Okay, I will say for SBCL it is. I've used it before, and as far as I've seen, I haven't had any issues with Unwind Protect in thread safe code. And honestly, Michael Gargano, because you brought it up, while it is true that Common Lisp, the standard, does not specify concurrency, recent developments have actually created, I would say, enough de facto libraries for it that we will be discussing concurrency in a couple of weeks, because I think it's something that should be discussed at least. It's on the schedule. We'll be talking about specifically like Bordeaux threads and L parallel, which honestly two libraries that are often ignored. There's too many concurrency Stack Overflow articles in Common Lisp that where I can honestly say no one, either Bordeaux threads will get brought up or L parallel will be brought up, but neither are brought up in the same thing, and they're both available and they're both useful in the right context. So, but that's a discussion for a different day. That's a long discussion, honestly, because we would have to discuss how concurrency actually works in the Lisp virtual machine and what's available to you to leverage those primitives first. But to make a long story short, though, Unwind Protect in at least SBCL, I'm kind of certain about Clojure Common Lisp, and I'm almost certain about Allegro Common Lisp too as well, because Allegro uses it quite a bit. In those three cases, just this is from my personal experience, Unwind Protect is thread safe, but that's probably based on very primitive Lisp code that I've written. I haven't written sufficient enough of low-level threading code in Common Lisp to really say that I hit some sort of limitation in that implementation. So take that with a grain of salt based on your use case. If you're doing like any sort of crazy mutex shared memory programming, especially, that's where that breaks down, because I've often tried to do more like a fan in, fan out, which is, give a dedicated chunk of memory, have the thread access that memory independently of all the other threads, and I made sure that I broke up the work items to do that computation, and then I fan back in and actually just reduce them. So those in that situation, because they're always kind of chunking in an independent way, you will never hit the contention issue which is where threading breaks down in any sort of low-level library construct. If you ever dealt with things like mutexes and condition variables especially, and dealt trying to implement producer-consumer stuff, you'll know what I'm talking about. And that's something I will be at least discussing later on, because we're getting to a point where that's going to be very important to talk about. Does that make sense? No problem. Because you brought it up, though, one thing I wanted to kind of ask around, at least folks in this discussion, like, how much experience have any of you had with just writing concurrent programs? I mean, I've done it enough that I have some basic examples that I can go through, but I wanted to at least get the consensus across the rest of the audience that are at least available here. Okay, cool. Judd, have you touched any? I think he's probably not paying attention. Have you ever done any concurrent programming? Okay. And Michael Fiano, I'm assuming you have. Wow, that's uncharted territory for you. I'm surprised. Okay, because all right, cool. Because that will be a fun discussion. I think knowing what's available in Common Lisp for concurrent programming will really blow your minds because of what's available there. But I'll discuss that, and I need another like 2 hours to discuss that with you. Uh, all right. um, Bottom line, folks, regarding Unwind Protect that I want to bring up, and I know I've said this enough, but I'm going to say it again. Use it. That's and it's not even a suggestion. If you're doing any sort of resource management or anything where you're going to be dealing with some operating system resource, whether it be a socket or a file or a database connection or any of your custom objects, or you're creating something where you're going to be dealing with having to open something, do operations, and closing it, or require that an operation always be changed, even in the most exceptional of situations, Unwind Protect guarantees that cleanup form will be run before it exits. That's guaranteed. So just use it. I mean, I can't say that anymore. Just go ahead and leverage that particular operator itself, and the fact that it didn't get enough like visibility even now like kind of upsets me, but what can you do? The last part of Peter's chapter is stuff that we've already talked about multiple values, things like multiple value call and multiple value list, for example. We touched base with multiple values in general, like multiple value bind. I don't think I have to show an example of that again. But one thing that is kind of useful is multiple value call. If you're like dealing with like element by element function calls. So let's say that you have two different collections that you want to actually run through and do a summation on. What you can try doing is some people try to do, like, let's say that we're adding two different lists. Let's say that we are adding two different lists and we have values 1, 2 and values 3, 4. If you think that this is going to add 1 to 3 and 2 to 4 and then summing it, you would be actually wrong. And there's a reason for that. And oh, right, I didn't put a sharp quote. Apologies. So if you run this, you'll see that what's actually spat out by SBCL is actually 4. For folks who can't see my mini buffer, I should actually go and just shoot it out to a buffer. But if we actually go ahead and use multiple value call, this essentially says, okay, I'm going to do a fun call where I take the first argument from the first list and the second argument from the second list. And if we run this, you'll see that it'll actually go through and do the element by element addition and then does a truncation. It's almost as if it does the two dimensions where it does, a map and then a reduce, which I think was, I thought it was pretty cool. The same thing can be done with, and of course we've talked about, multiple value bind, but, just in case you guys forgotten, you have, two values. Let's say we're just, spitting out this guy. You'll see, oops, I think I typed in, value, not values. You'll see that, we have, we actually go ahead and add 1 plus 2 and, create 3. Multiple value list is something I've honestly never actually used. Wow. Multiple value prog 1. Yeah, that one is in the footnotes that I saw before, and I was like, I'm not entirely sure when is that even leveraged. Multiple value list, all it does is when you spit out values, folks, if you ever use values from a function, it'll actually spit them one at a time. Okay, this is how values is actually printed out to the console. What multiple values list does is it actually goes ahead and takes those and creates a new list for you. So if you run this guy in the REPL, you'll see it returns a proper list for you. It doesn't actually do one at a time. If you call value list, values list on multiple values list, you'll see it'll go back to values. So you can see how things are now changed together actually. It'll create a new list, generate it, and then change it again. When will you use it? I'm guessing when you're spitting out multiple values and you want to do like a reduction on the list. Honestly, I have to think about that as to when this kind of construction, destruction, construction again is kind of useful. But bottom line is if you need to actually aggregate results and you're getting multiple values from a function, you need to aggregate all of them. You don't need to iterate through and put them in your own collection. You have a function that will actually go ahead and do it for you. The last but I don't know. Actually, you're talking about using multiple value lists to actually do what now? To map the results of a function? Oh yes, that actually makes sense. Yes, yeah, that makes sense. So you're talking about like something like this map car, and you need to pass in some sort of lambda function, and you're passing in the multiple value list. You're right. That actually would work. This is definitely, like I said, there's things in here that have uses. I've never had in my day-to-day, I've never actually leveraged them. Yeah, absolutely. There's a lot of cases where this is useful, but I'm just mentioning from my own personal experience on it. It's not that I'm not saying that it's not useful. I'm saying that I've never had any use for it. From my own use cases. But certainly it's available for anybody who has particular use cases for it, And you can see that, transforming data from one function that passes in multiple values is certainly a good use case for it. Yeah, this one. This is particularly useful. So the very last special operator that we're going to be touching base with is actually an operator that how can I explain it? So there might be times where you might have okay, yes, eval when. How do you explain eval when? So eval when, okay, so let me start by first talking about how we load stuff into Lisp. Okay, when you load stuff into Lisp, you normally load it through either a load file or you compile it and load in what's called a FASL. And the FASL is what's in a form called a fast assembler. It's like a bytecode that Lisp actually compiles into its own machine code representation based on the compiler that you're actually leveraging. What eval when does is it actually gives you the ability to evaluate when certain things need to be loaded and when when things need to be defined and when they need to be defined. So there's three different types of situations where this kind of evaluation control is necessary. When you're actually compiling the system, all right, when you're actually loading up the system for the first time, which is when you're loading up FASL files, and when you're actually executing the system itself. So the form that you would normally see, and this is often used in, is loading up libraries. So you might see execute, compile, top level, or I've seen often eval when, execute, load top level separately, so that if there's different libraries that you want to do. And what this does is it allows you to like conditionally compile and conditionally load certain types of libraries, as well as define certain types of functions that you might need in different situations. Like if you have debugging functions, for example, that might be useful for compile top level, but it's not useful at all when you're executing. That you may just want to log something instead of actually printing out debug statements or having functions that define debugging. So I often leverage this to load libraries and to define like debug functions that get essentially, it's not technically tree shaking, but it's essentially we're ripped out of the production build when it's actually being run. But there are other cases where this is there are uses. Good to know. Interesting. True. Okay, right. That's a very good point. Um, I wouldn't use it in that situation, right? Like I said, but that's a band-aid for a specific situation where people actually did it wrong, right? Right. Yeah, those folks that are doing it that way, that means that they don't want to re-architect a particular part of their solution. And that's kind of, in my opinion, it's wrong. Fundamentally, it's wrong. You should re-architect when you see a problem like that. Most people never re-architect when they see limitations in their design, and that's kind of just in general, that's bad software engineering practice. But there's not much you can do if you tell them, look, this is going to cause more trouble than just moving it over to a different file. You know what I'm saying? It's really up to them. But that doesn't show it doesn't dismiss the utility of eval when to use it and how to use it. There's particular cases where it's actually very, very useful, and um, most often than not, it's when when you're trying to separate certain, like, library linking um, and usage of libraries at certain stages of the development of the Lisp application. Um, Often there are people who misuse these kinds of things for other things, and that's, I would say, is a misuse. So, um, so there's a lot of other functions that are available, a lot of other special operators like locally, load time value, and progv. But I'll be honest with you, I have never used any of these. Um, uh, it's not. I'm not saying that there's potentially a situation where they're kind of useful. Um, like load time value. One quick example of that is just basically, it's just, it creates a load. So when something is loaded and it's compiled, it generates this load time value form that you could then get the universal time from a global variable. Is it useful? I don't know. I don't know when. I would never use it. But as Peter actually rightfully said, most of these are very, very rarely used. progv especially I'll never use, and I don't encourage you to use it because it deals with dynamic bindings for variables. And I almost try to encourage you to never use dynamically scoped variables unless you're doing concurrency. That's the only situation in Lisp where I'm like, if you're doing concurrency, you need thread local storage, and if you need since you need thread local storage, there's nothing better than using a dynamically scoped variable because it's the same thing as if you're creating your own, thread local storage on the operating system. But again, uh, we'll be discussing that in a different in a different talk altogether. Any questions? $15 out of 25. That's still not bad if you think about it, right? 75%. I mean, no, wait, no, it's 60%. 60%. It's 60% is not that bad. Yeah, but the one thing that I honestly today will have completely been confused when I learned Common Lisp is still the the operator, the. That operator, I don't know what the person who made that operator was thinking. Yeah, just the name, just the name. Like if I saw that in code, I would be like, I would just stare at it for 10 minutes. And I'm like, okay, I understand that you're saying the object, but what is the doing? uh, okay, guys. Before I let you guys go, I wanted to say that next week, we will not be having the Common Lisp Study Group. Just a quick announcement. Primarily because next week is finals week for me, so I need that time to prepare for finals. So we will and next week is also, if you think about it, the Game Jam. Yeah. So the Game Jam is on the 20th. It's starting this weekend. I hope you guys are going to have fun with it. I unfortunately will be unable to join this time around. But look forward to our to the week after, where we continue our discussions on PCL, and we're actually getting to a good real project. We have two primary remaining issues. One of them is related to packages and dealing with packages. And honestly, I'm going to give you guys a proper package tutorial. Peter only gives you a very small introduction and doesn't do it enough justice. And I think there's a bigger discussion when you were talking about packages and visibility that needs to be discussed about. But until 2 weeks from now, thank you guys for joining me, and I'll see you next time. Thanks.